Hello and welcome to this short tech talk. My name is David Espejo. I'm based out in Colombia, South America, and I've been part of the vBrownBag community for quite some years now. So I'm very happy to be here with you sharing these topics. In this session, I will share some history around how the data persistency models have evolved in the Kubernetes design throughout the years. So let's get started. Well, first of all, the origin of this history was Kubernetes needed a way to handle the provisioning or consumption of storage, right? So this system, no matter if it was born inside Google or how it has evolved outside of Google, it has always needed a way to handle storage consumption. So the first notion of this was the static provisioning, that is even not here in the presentation. That is step 0, static provisioning. So Kubernetes could only handle mount and unmount operation, but someone else will have to provision the storage for Kubernetes. So then it came dynamic provisioning, which is a way to connect the pod API. The pod is the basic execution unit in Kubernetes. It's like the VM, let's say, in a vSphere environment. So dynamic provisioning is a way to connect the pod object to a system that provides storage, right? So it's dynamic because it responds to a different logic than just a manual mount or unmount operation. So there are two ways to provide dynamic provisioning to Kubernetes. The first of all was internal or in-tree. So internal is the kind of volumes or storage that Kubernetes can create by itself. So Kubernetes was not born thinking on data persistency, because most of the applications designed to run on top of it are stateless or were stateless. So data persistency was not the priority, let's say. So the internal dynamic provisioning or in-tree storage services were pretty much limited in functions. And when Kubernetes was released to the world, was donated to the CNCF in 2015. The first option for storage providers was to write code and to ship and CNCF to communicate with the storage provider in order to merge that code into Kubernetes itself. So you can imagine how hard can be that to manage at scale, and that affected the agility of the release cycles of Kubernetes. So there was another way that is the external or out-of-tree dynamic provisioning, in which Kubernetes provides the pod a way to connect to an external or custom provisioner created by a specialized storage vendor. So that's great, but it's not complete because it provides just a limited set of options. And there's a question remaining out there, and it's how to translate the different storage requirements for my applications to this limited set of functions. So if you go to a virtualized data center, probably you will agree with me that all of the applications deployed there in the VMs, not all of them require the same in terms of storage. Some applications require low latency, extremely high performance. Some other types of applications are not latency sensitive but require more capacity or more reliability or durability, etc. So there is a diverse set of requirements, and just having the storage management inside Kubernetes, it's a limited way to achieve those requirements. So A little step ahead was the creation of the volume type called flex volume. Why flex? Because it's let's say it's a plugin. It's a plugin to communicate the pod API. Again, the pod is the execution unit for Kubernetes, to communicate the pod API with external storage drivers. So that's great. The thing is that Flex Volume, it has to be installed in every single node of the Kubernetes cluster. And that implies that it's part of the execution environment or part of the execution scenario, let's say, or execution namespace, let's say, for Kubernetes. It's like installing a driver or a plugin in your ESXi node. It's great, but if that driver happens to have a compatibility problem with ESXi, it will take down your node. So it's not great to have the plugins there, at least in Kubernetes. And all of that just to have attached and detached operations. So it was a little step forward, but not enough. So that prompted the CNCF and Kubernetes community to develop an specification, a complete set of or a protocol to define data models for Kubernetes, and that is the CSI, Container Storage Interface. It's a way to create, let's say, cloud native storage, right? So what is the main idea behind CSI? Decoupling the storage management from Kubernetes, right? So there are many components in a Kubernetes cluster, but there is one that runs on every node in the cluster, which is the kubelet. The kubelet is, let's say, the agent that runs on any node. So the CSI is the massive undertaking of decoupling storage management from Kubernetes, but letting a bridge or a way for the kubelet to be able to find the volumes and mount the volumes, and that's it. But Kubernetes won't be responsible for create them, destroy them, manage them, not a single bit of that. So that is important, because when you combine that with dynamic provisioning, if I take a step backwards, let's say, dynamic provisioning requires the use of a concept in Kubernetes that is called storage class. Storage class, it's, let's say, like a storage policy or storage profile in vSphere. Let's say it's a way to specify these are the requirements or the features I need in this specific type of storage for this specific type of applications. You can have several storage classes, as you can have several storage policies or profiles in vSphere. So storage classes are a declarative way of defining requirements for storage. So if you combine that with CSI, you can have a very flexible and also scalable model of handling storage, because you can define in a flexible way your requirements, and also you can manage the storage in a logic separate from Kubernetes. So you will be able, for example, to upgrade the Kubernetes cluster without having to upgrade the storage components. So that is very important. So in a, let's say, graphical way, I found this diagram clear enough from the guys at the New Stack magazine. And, in this diagram, the developers just require storage for the application, and that's it. The application run in pods, and the developers request storage using a construct called PVC, persistent volume claim. It's a way to define the storage requirements. And in both approaches, dynamic storage will fulfill the requirement. The end result probably is the same. In the right-hand side, CSI, it's kind of a bit more complex, but you can see there that is decoupled. In the left-hand side, you will see a volume controller inside Kubernetes, right? So there is external code running inside Kubernetes. So that has this limited set of features that I talked previously. So when the developer performs the request, the API server, which is kind of the gateway, or let's say like a vCenter server, the API server will receive the request, and the volume controller in the in-tree approach will find if there is a volume already created with those requirements, and if that's the case, it will publish or it will assign that volume to that pod, right? The kubelet, in both cases, the kubelet will perform the mount operation. In the CSI world, in the right-hand side, there is an external provisioner. This is provided by your storage vendor, right? So your storage solution for Kubernetes, be it in the public cloud or on-prem, should have a CSI compatible solution. It will provide an external provisioner, which happens to be another pod running in the cluster, probably in a different namespace, but running in the cluster. It will respond to the request, and Kubernetes or the kubelet just perform the mount operation, right? So all the logic, this is a simple operation. This diagram is pretty much simple because it only mentions the mount operation. But the more mature drivers or CSI drivers these days provide not only mount or unmount, they can create the volume, mount the volume, resize the volume without affecting the applications, snapshot, restore the volume, unmount the volume, and destroy the volume. So all the life cycle of the external storage is managed by the CSI driver. So in this way, you can scale Kubernetes and keep the storage management separate from that. Right? So how can I know if my storage solution or my cloud provider has different features in the CSI driver? There's a public list in the Kubernetes documentation. You can just Google Kubernetes CSI drivers, and you will find here a list. This is just a snapshot of the list. You will find here a list of all the vendors or cloud providers, the current versions of their CSI drivers, and the features they provide. So it's important to check this when you're, researching platforms to run a Kubernetes environment. Right? So I hope that's clear. I appreciate so much your time, and thank you for watching.